So welcome to part 2 of the concepts. So let's look at some new things. So impedances. So what are impedances? So how we relate resistors with ohms. That's great that they can interact with each other, but we want to know how a capacitor, an inductor, and a resistor all can interact within the same circuit. So the way we relate those is by these concepts called impedances. And we represent these with the symbol L. And our unit for impedance is going to be ohms. So you can think of it as these capacitors and inductors as not having a resistance, but having an impedance, having some form of a resistance. They're kind of impeding things from happening within the circuit. So let's take a look. So resistors. So if I write the impedance of a resistor is just going to be the value of the resistance. And of course, the unit is just ohms. So what does that mean? Let's take a look at it. So we have a resistor. We'll say that's 10 ohms. Therefore, our impedance value will equal 10 at an angle of 0 ohms. This is the real part of it. Okay. Notice that we're pulling that phase angle in there. It's an angle. So the angle is 0 for a resistor. Let's go take a look at a capacitor. It's going to be a little bit different now. So a capacitor, we use this concept called ice. And for inductors, we use it for Eli. Okay. And a way to remember this is Eli the Iceman. And each one of these has a meaning. So whereas we have that phase angle, so that angle right there, we said that's a phase angle. And what does that mean, though? Because we just keep talking about it, but we really don't know what it is quite yet. So we have current, which equals to I. Then we have voltage, and we write that as E. So in an inductor and a capacitor, they're going to interact differently. So from our phase here, we see that there's this current and this voltage. And in the middle here, there's a C, and the C is going to be representing a capacitor. So what this phrase means is current leads voltage in a capacitor. And I'm just going to shorthand it like that. Okay? So what does that mean for us? What does that actually look like? We can think of it like the real and the imaginary graph that we had drawn before. So if I drew this out here, where this is at a 90-degree angle. So ideally, right here, what this is 90 degrees. So we can imagine that this voltage here is following that current, and it's following it at an angle of 90 degrees. So it's 90 degrees behind the current. So our angle here is negative 90 degrees. So we want voltage here. Okay, because remember that we are trying to find the voltage through this. An important concept that we need to know. Well, first I'm going to just write this out real quick. Just my shorthand notation for the rest of the videos. How do we find the impedance of a capacitor, though? So we need a couple things to find the impedance. The equation, which is going to be on an equation sheet, is 1 over j omega times c. This is also equal to negative j over omega c. So therefore, you can say the voltage in the capacitance is equal to the inductance times the current in the capacitance. And that looks very familiar to our Ohm's law. But now instead of resistance, we have impedance. And that is A-okay with us. We can do that. But I'm going to make this note up here. Remember, we had j squared is equal to negative 1. And from this here, we can see that 1 over j is equal to negative j. That is a very important relation as well. So just keep those in mind as you're doing these problems and learning these concepts. So let's look at the inductor now. So the inductor is going to have voltage, current, and L stands for the inductor. So now voltage leads current in an inductor. I'm just going to write IND. So looking at that, what does that mean for us? Well, if we go and draw our graph here, current is back here, inductor is in front of it, and ideally that's 90 degrees. And like we said, we want the voltage. So positive 90 degrees. That's what we're going to have for the inductor. And our equation for the impedance for the inductor is also going to be on the formula sheet. It's just j omega L. So therefore, V of L is equal to Z L I L, which just looks like our Ohm's law once again. So it makes our calculations a lot easier this way, and we get to bypass a lot of the more complex equations that we saw with exam 2. Let's look at some combinations that we have. So since these are impedances are in units of ohms, we now get to treat everything like resistor rules. So we get to sum, let me write this, write it like this. So Z in series will be equal to the sum of the impedances, which should just be Z1 plus Z2 plus Z3 plus dot dot dot. But we can also write it like this. This is just another way of representing it. ZR plus ZC plus ZL. And all we're doing is just taking whatever combination of resistors, capacitors, and inductors and converting them into impedances, and we can combine them like they're resistors. Okay. What about parallel? So parallel, like we said, these are in units of ohms. So these are also like resistor rules. So Z parallel will just be equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot dot dot. And then, of course, if we have the there's two z's, you can do z1 times z2 over z1 plus z2. So like we said, it's just all the resistor rules just repeated. And I just want to remind you once again, draw one more time, j squared is equal to -1. 1 over j is equal to -j. Those are very important. All right, so it looks like that'll do it for our concepts. I'll see you in the next video when we start working some problems out.